Hello guys, today we are discussing the Bose Einstein statistics and Bose Einstein distribution law. In B statistics, particles are indistinguishable, that is, they lose their individuality. Obviously, one must concentrate the attention on the cell rather than the individual particles. Each cell may occupy any number of particles, and hence, in this case, one can three possible arrangements. This statistics for the many particles system was first proposed by Bose in 1924, who applied it to photon gas, and the same year it was modified by Einstein, who applied it to gases. It is why this statistics is called Bose Einstein statistics. The statistics is applicable to the like or indistinguishable particles having spin 0 or integer. These are called bosons. We have seen that in Maxwell-Boltzmann statistics, the particles are distinguishable from one another. If two particles interchange their position or energy states, a new complexion would occur. But in B statistics, particles are identical and indistinguishable. Obviously, the interchange of two particles between the two energy states will now give rise to new complexion or microstates. In order to derive the B distribution law, we require or we know to some assumptions of the B statistics. The first one, the particles of the systems are all identical and indistinguishable. There can be any number of particles in any quantum state or phase cell. It means there is no restriction on the number of particles in a cell. The sum of energies of all the particles in all quantum states is equal to the total energy of the system, which remains constant. The number of phase cells is comparable to the number of particles in the system. It means the occupation of the index is nearly unity, that is Ni over Gi is equal to 1. The spin angular momentum of the particle is integer, that is including 0, multiple of where h is the Planck's constant. To derive the B statistics and distribution law, let us consider a system having the total number of particles in the system Bn. These particles are all alike and have integer spin. Every particle has a definite energy and momentum can be represented by a point in the phase space. To determine the maximum probable distribution, we divide groups or the available phase space into a large number of quantum groups or energy levels. These groups are further subdivided into cell of volume h cube. The cells or the number of phase cells Gi in an energy level, that is the epsilon I, or we can say simple EI, represents its degeneracy or the statistical weightage. The statistic is nothing but the count. Here it is assumed that the number of cells is comparable to the number of particles and it is very large. Let the degeneracy of the energy levels, that is E1, E2, E3, etc., be a G1, G2, G3 up to etc., and also let the number of particles in them be. So the equation set with the total number of particles, and the total number of particles is nothing but n1 plus n2 plus n3 up to ni plus up to or so on, that equals to summation ni, and that is equal to n, and which is constant for the system, and the total energy of the system is also E, and we get n1 E1 plus n2 E2 plus n3 E3 plus ni EI is equal to summation ni EI, and that is equal to E, that is constant for the system. Now consider the ith energy level having energy EI with degeneracy Gi and having the Ni particles in it. First we try to find out how these Ni particles are distributed in the Gi cells. The first cell can be chosen in Gi ways. Now remaining cells are Gi minus 1, and with the N2 particles there are Ni, or we can say yes, it is a Ni plus Gi minus 1, because we are considering the Ni and Gi elements which can be arranged in Ni plus Gi minus 1 factorial ways. Thus the total number of meaningful ways in which Ni particles can be arranged in Gi cell is, but the total number of arrangements will be Gi into Ni plus Gi minus 1 factorial, but all the particles are identical. Therefore, rearrangement among themselves, that is their permutation, Ni factorial, will be meaningless. Similarly, the permutation of Gi cells, that is the Gi factorial, will also be meaningless or meaningless. So, the number of meaningful ways in which Ni particles can be arranged Gi cells is given by the probability of I is equal to Gi in bracket Ni plus Gi minus 1 factorial over Ni factorial into Gi factorial. Or we get rearrange it, we get the probability of I is equal to Ni plus Gi minus 1 factorial over Ni into Gi minus 1. So it is represented as equation number 3. Similar expression will be obtained for other energy group also. Therefore, the total number of ways in which n particles can be arranged in various energy level and is given by the probability is equal to the probability first into probability 2 into probability 3 up to probability I and so on. So substitute the value of probability 1. This value is for 1, then second for this, then third for this, and take the product, that is the multiplication of terms. So we get, just I am substituting the total probability of the system is equal to, for 1, that is the n1 plus g1 minus ni factorial over ni factorial into gi minus g1 minus 1 factorial into second probability, that is n2, and so on. Then we get, this is the multiplication of terms. So probability I for the whole system is equal to the product of all the probabilities. We get ni plus gi minus 1 factorial over ni factorial into gi minus 1 factorial, equation number 4. So this represents the multiplication of terms. The numbers ni and gi are very large, so we can drop 1 in comparison to them. So that we get the equation, the probability is equal to the multiplication term by I into ni plus gi factorial over ni gi. It gives the equation number 5. Now once we get this probability, so we can easily find out the most probable distribution. For that purpose, take the log on both sides of the equation. So log of probability is equal to summation I in bracket log ni plus gi factorial minus log base e into ni factorial minus log gi factorial, equation number 6. So for this term we can use the Stirling's formula. So by using the Stirling formula, the log e factorial n log e or log ni factorial is equal to n log n minus n. So substitute this value. By using the Stirling's formula, we get the log of probability is equal to summation I ni plus gi into log into ni plus gi minus ni plus gi minus in bracket ni log e to the base ni minus ni minus, then again here we are using the Stirling's formula, so we get gi log of gi minus gi. Rearrange it, so we get summation I ni plus gi log of ni plus gi minus n I log ni minus gi log gi, equation number 7. The number of cells in a state gi remains constant while ni varies. Therefore on differentiating equation 6 we get summation I or the d log of probability is equal to summation I log e gi plus ni into dni plus ni plus gi 1 divided by ni plus gi dni minus log ni dni minus ni 1 divided by ni into dni. By rearranging, we get d log probability is equal to summation I log e ni plus gi log of e ni into dni. So d log probability is equal to summation log into ni plus gi by ni into dni is equal to 0. That is equation number 8. In the equivalent state, which is also the most probable state, the value of d or the value of probability, change in probability, and hence this term becomes 0. So d log of probability is equal to 0. So the terms becomes summation I log e ni plus gi over ni into dni is equal to 0. So there are two identical conditions imposed on the system, that is the summation ni is equal to n is equal to constant. So the total number of the particles in the system is constant with their numbers. So summation I ni is equal to n is equal to constant, so summation dni is equal to 0. Similarly, for the second, the total energy of the system is also constant, so we get summation I f long I dni is equal to 0. So this f long dni is nothing but the summation of ni into f long I is equal to E is equal to constant. So this term is nothing but the energy of the system, which is remains constant. Now the equation 9, 10 and 11 are independent of each other, but must be satisfied simultaneously in the equilibrium state. So we use the Lagrange method of undetermined multipliers. So multiply the equation 10 by a log A and equation 11 by minus beta, and then on adding the resulting expression to equation number 9, we get the summation I is equal to log of ni plus gi by ni minus log of A minus beta f log I whole bracket close dni is equal to 0. So here dni is available or a variable quantity and is not necessarily 0. In order to this equation may always be satisfied, it is necessary that the coefficient of each should be separately 0. So we get the log of E ni plus gi over ni minus log of E A log of base E A minus beta f log I is equal to 0. So just rearrange it. So we get the log of E in bracket ni plus gi over A and I is equal to beta f log I. Again rearrange it. So log goes to this side. So we get ni plus gi by A and I is equal to log e to the power of beta f log I. Again rearrange it. So this value a and I divided by a and I is cancel. So we get 1 plus gi by ni is equal to a goes to the side, a to the power of e to a into e to the power of beta f log I. Then 1 goes to this side, so gi over ni is equal to ae raised to beta f log I minus 1. Then ni is equal to gi divided by ae beta f log I minus 1. So this is the Bose Einstein's law, which gives the number of particles in the ith quantum state with the bosons. So here the term a is equal to e raised to alpha, where alpha is the another constant, then it becomes ni is equal to gi divided by alpha plus beta f log I minus 1. So this is the this is the Bose Einstein's distribution law. In many applications of B distribution law is used in this form. If for the quantum states the difference in the energy level is very small, that is the distribution is a quasi-continuous, then the energy interval from f long to f long plus d f long, we can replace the degeneracy factor gi by g into f long into d f long, where g f long is the density of energy states. That is, energy density is nothing but the number of energy levels per unit interval of energy. Thus the number of particles in this energy interval is n f long df long is equal to g f long df long divided by ae raised to b f long minus 1. So this is the B statistics. I hope you understand all these things. If you have any queries, please ask me frankly. Thank you for watching this session.